good morning and welcome to the last lecture of this particular short-term course. I'm happy to be the person to be in the last because we have so many people who are experts in the field of flow visualization and optics, and it's good to get a basic introduction and also something about the other flow visualization techniques. And as a conclusion, I would like to talk a little bit about the thermal imaging, which is also increasingly used by research scholars who are especially interested in looking at the thermal picture, the thermal maps or the temperature maps accompanying the flow field. And sometimes it can also be an alternative to flow visualization. I will give an example how we in fact used thermography first before we got something interesting to do flow visualization. So before we get started, so how many of you here have already used IR camera for measuring temperature before, or you are planning to use it in your research? Can we just see 1, 2, 3, 4, 5, 6, 7, 8? Yeah. So out of 8, I think 1 is my student, so I will just discount him. But okay, so not bad. So basically, some of you have already used it. So, and many of you are already familiar with it, and more familiar than probably the techniques like interferometry and DFT and so on. So I will just give some very brief introduction about infrared imaging, the different types of detectors, and then go into the techniques that especially I as in my research group are using IR cameras for. Okay, so basically the concept of thermal radiation is important. So I'm just giving a slide here which explains this particular issue. So when you're looking at matter, it could be solid, gases or liquids. So atoms and molecules, and once the temperature is above 0 Kelvin, so these atoms and molecules will have a random motion, so collision between each other and so on. And you know that these molecules and atoms also have electrons. These are the charged particles, right? Electrons and protons. So when according to the movement of these molecules, you also have movement of these charged particles, and once movement of charged particles happens, what happens? So you have electromagnetic radiation. So this is basically the principle how electromagnetic radiation is associated with movement of particles like molecules or atoms. And any of the system above 0 Kelvin can have this kind of a random motion, and the higher the temperature, the greater is the motion of these particles, velocity at which these particles move randomly, and consequently the emission of electromagnetic radiation will also become significantly higher. So this is the basic principle. So you should not confuse this with the diffusion, so which usually happens. In the case of diffusion, for example, associated with temperature, you need a temperature gradient for the diffusion to happen, and the diffusion process will transfer the heat from the higher temperature to the low temperature. Same thing applies to mass transfer as well, as a function of the concentration gradient. So this is more like a Brownian motion, you can say, and on top of which when you are looking inside the molecules, the Brownian motion stops with what happens to the motion, random motion of these atoms and molecules. Now with radiation, you are going inside and seeing associated with this random motion is also the motion of charged particles, which is basically the contributing to the radiation, electromagnetic waves that we are talking about. Therefore, any substance which is at a temperature more than 0 Kelvin has a thermal motion and can emit radiation. So this is very important, because when we study heat transfer, we look at radiation independently as though that this is an independent mode of heat transfer. But you should understand that all bodies at temperatures greater than 0 Kelvin will participate in heat transfer through radiation, apart from the other modes of heat transfer such as conduction and convection. So, and you should also understand when we talk about electromagnetics, we also look into the dual nature. So for example, if you look at the electromagnetic spectrum, we consider this as waves for certain convenience to study, make use of the wave effects that Nambudiri was discussing during the first day. And we also conveniently look at particle nature. So when we want to look at the quantum physics, do some statistical thermodynamics, get some things such as the Planck's distribution, and so on. So we exploit the particle nature of this light or any electromagnetic spectrum. So therefore, as the thermal motion increases, you can see that as you go from the left to the right, so here you are considering this as a indicator of increasing temperature scale. You see the thermal motion increases and consequently the frequency of the vibration of the electromagnetic waves increases and consequently the energy associated with these electromagnetic waves also increases. So this is the principle by which we use any detector to detect the electromagnetic waves that are falling on the detector and then mapping that as a function of temperature. And from the quantum theory also, you know that if you consider the particle nature of these electromagnetic waves called photons, we say that the energy is a function of the frequency. So higher the frequency, higher is the energy. So both these perspectives are important. So you should know where to use them. So both these perspectives exist in fact in nature. So this is the dual nature of both light and particles. And we will see. For example, when we look at the electromagnetic spectrum, we treat them as waves, right? And electromagnetic spectrum is quite large. So you can look at spectrum from the left, which starts with gamma rays, and with very high large wavelengths you go to as large as the wavelengths of radio waves. And the visible spectrum that we are mostly talking about when we are dealing with most of the optical imaging techniques, so they are in a very narrow band of 400 to 700 nanometers or zero point 0.4 to 0.7 microns. So this is a very narrow band, and consequently we'll see why our human eye is only sensitive to this particular band. It's going to be answered by the Planck's distribution of emissive power. So we will see that if you approximate the sun as a black body, so the peak emission from the black body at the temperature corresponding to the surface temperature of the sun happens to coincide with this visible band, and so therefore it's not a coincidence that our eyes are tuned to be more sensitive to that particular band. So this is the design of the nature, you can say. So and however, when we are now concerned about the thermal imaging, so we are not going to be working with the visible spectrum. We are going to go to slightly longer wavelengths which are in the infrared band. So therefore, visible wavelength is a very short period which is between 0.4 to 0.7 micron wavelength. Infrared band is quite large relatively, and it can span anywhere from the near infrared, which starts just after the visible spectrum gets over at 0.7 micron, to as large as far infrared, which can go up to the order of 100 to a few thousand micrometers. So let us see what is the band that is suitable for infrared imaging as far as the temperature imaging is concerned. So as I was talking about the Planck's distribution function, so this is the plot which shows the Planck's distribution function where the spectral intensity, that is the intensity as a function of wavelength, is plotted for different temperatures. So assuming that you have a black body, so this was actually obtained by Max Planck, and again for this quantum mechanical perspective was very useful because so assuming that these photons are particles and then using the Bose-Einstein distribution function to describe these photons, so you can actually derive the Planck's distribution function. And so this tells you that the larger the temperature of the body, the sensitivity or the peak of this emissive power shift towards smaller wavelengths. Okay, so and as you go towards larger wavelengths, this the peak, the temperature, the peak sensitivity of this shift towards the bodies with smaller temperature. So therefore, if you look at sun with an approximate surface temperature of around 5700 Kelvin, and you approximate this as a black body, you see the sensitivity corresponds to the maximum intensity of emission coming from the sun falls around the visible spectrum. Whereas if you go to around 300 Kelvin, for example, so this is mostly going to be sensitive in the infrared region. So this is where you see around wavelengths of 5 microns, 6 microns, and therefore if you are looking at imaging the objects which are close to room temperature or slightly above room temperature, infrared imaging will be the most suitable imaging possible. And it's not just simple here. If you look at infrared imaging, now that you decide that infrared is a good technique to probably do a thermal imaging, what do you then look for is when you're putting a camera in front of the object that you're imaging. So the infrared is going from the specimen into the camera through a layer of the atmosphere, right? So now you need to know what is the transmissivity of atmosphere, which is also called as the atmospheric window, which can be transmissive to the infrared radiation. So if you look at this, this is a plot of the atmospheric transmission as a percentage. 100% means that it is completely transmissive to infrared, to different wavelengths, and you can see the wavelengths. Here we are particularly concerned about the infrared band. Okay, you can see atmosphere here has so many constituents. You have water vapor molecules, you have oxygen, you have ozone, and you have other constituent elements of atmosphere. Most of the absorption of the infrared happens due to the water vapor molecule, right? So therefore, when we look at the windows which completely allow the infrared, so nearly 80 to 90% and above transmission, these are the windows through which infrared can penetrate through water vapor. So this band which is close to the visible spectrum of the order of 1 to 3 microns. You can say this is in the short wave infrared spectrum, and the other band which you see is around 3 to 5 microns transmissivity, where the transmissivity is very high, is another window which is in the mid wave infrared. And then you have a region where the water vapor is completely absorbing all the infrared, and again you have another band from 8 to 14 microns which offers maximum transmissivity to IR. This is the long wave infrared. So therefore, when we are using cameras, we have to be sensitive to this information, and accordingly the cameras are designed to work either in the bands which allow the short wave infrared to pass through, or cameras which allow the mid wave infrared, or cameras which allow the long wave infrared. Now, so therefore, there are 3 different types of cameras overall when we look at infrared imaging. So these are the 3 different transmission windows through which you can look at infrared waves, and each of these have a different wavelength bands. Okay, now if you look at thermal imaging camera, how was it first developed? As just like most of the inventions, so I think the world wars were one of the triggers to invent this kind of techniques. And in 1929, the Hungarian physicist Tinai invented the infrared sensitive electronic television camera. This is primarily for surveillance and anti-aircraft defense in Britain. So now you look at the comparison here in this particular photograph between a normal visual image that you take with an optical camera, CCD camera, and the same image that you observe using an infrared camera. So you see a couple of things. For example, this person who is wearing glass, which is optically transparent. Now with the infrared you see that it is completely opaque to IR. So you see that is appearing a little, the glasses are appearing little darker. Here darker means lower temperature, because the glasses are cooler than the rest of his body. So therefore you see that the infrared radiation that is coming directly from the glass, because it is opaque, and the glasses are slightly cooler than the rest of his body temperature. You see that this is a slightly low temperature. And the other one that you see is plastic, which is opaque to normal visible wavelengths, is completely transparent to infrared. So you see that you are able to see directly the temperature of his hand, so you don't see the temperature coming from the plastic. So this is another important property. When you are doing infrared imaging, sometimes because we are so tuned to what we see with our eyes, we forget what happens to transmissivity of materials in the infrared regime. Okay, so objects which we think are transparent in the optical regime are in fact opaque in the infrared regime, and vice versa. And this is a good example of this. Okay, now coming to cameras, as I said, now you have these transmission windows. So we can have cameras which are sensitive only to the short wave infrared, cameras which are sensitive only to the mid wave, and those which are sensitive only to the long wave. And accordingly, there are different models available. For example, in our lab in heat transfer. So we particularly use these two cameras, the mid-wave IR camera, which is the FLIR X6981 SE. So this is a very high-speed camera, and this is also very highly sensitive. The other is a long-wave IR camera, which is the FLIR A655 SE. So both are scientific cameras. So they have a reasonably good resolution and good accuracy. The schematic representation of an IR camera basically is like this, just like you have any optical CCD cameras. So you have, instead of the wavelengths coming in the visual band, you have the thermal radiation which is coming in the infrared band, and you need an optical system to basically bring this and converge the thermal radiation to the detector or the sensor. So instead of a CCD device, you have a infrared detector or a sensor, and the detectors are different types. We will see that in the coming slides, but essentially, so you try to extract the electrical, the whatever infrared spectrum that falls on the sensor will produce or trigger an electrical signal, and this is processed by the software, and then finally you see that in terms of the thermal distribution in terms of some colors. So you again see a color distribution like what you saw here. For example, the purple color is the low temperature and the yellow color is basically the high temperature. So it converts the electrical signals again and gives a temperature scale depending on the intensity of the radiation that falls. So the lower intensity corresponding to low temperature is given close to a purple color, and then the high temperature which is high intensity signal is given a yellow color. So this is how the camera basically converts your infrared radiation into an equivalent thermal map or a thermal field. So in the sense, it is exactly not like a photograph. You don't have a film and then you don't converge the light into it and take it. So it is more like a CCD kind of a device. So here the sensor has to be sensitive to the infrared waves, and that should trigger these electrical signals. Okay. Now let us look at some of the advantages of each of these different types of cameras. So you are very much aware with different IR cameras that are in use. So we just not only use IR cameras for this temperature signature, but we also use for some other purposes like surveillance and so on. For example, the shortwave IR camera works mostly in the bandwidth of 1 to 3 microns. So this is the bandwidth of the shortwave IR. And one principal difference is there are some shortwave cameras which work on the concept of emission from the surfaces and capturing this emission by the detectors as the midwave and longwave IR does, but mostly the shortwave IRs work on reflected light from the objects, just like your normal visual cameras do. That means so your object is actually reflecting wavelengths, but in the shortwave IR band. Okay, and then the sensor is basically collecting this particular reflected light from the object in the shortwave IR band, and then you see things which probably are not visible to the eye, in the optical wavelengths, are now becoming sensitive when you image the same in the shortwave IR band. So that's what basically it does. So they also look similar to your black and white photographs of visual images. So sometimes you get even confused whether these are IR images or basically optical images. But you can see the difference where the IR imaging works here. For example, so let me start with the example on the right. So this is a photograph, of a city landscape where you have some smoke coming out, and then you see through it. When in the visible wavelength, the smoke absorbs the visible band, and therefore because of the scattering also, you don't see clearly through this particular smoke or haze. Now using the same, you can image the same with the shortwave IR, and you can see that you are completely, the smoke or haze is transparent to the shortwave IR, and you can see through the haze, and you can see all the finer details behind the smoke and haze here. So this is again because the shortwave IR has wavelengths which are slightly longer than the visible wavelengths. So therefore the Mie and Rayleigh scattering effects when it passes through the haze is much lesser than what the visible light does. So therefore in the end, due to the suppressed scattering, you will be able to see more clearly through the things like fog or haze or cloud cover to a great extent. But again, if it is a very thick cloud cover or a very thick haze, again this can scatter the shortwave IR also. But this is one fine example of how you can use the shortwave IR. So the same can be applied. This is probably the one of the bridges. It should be San Francisco. I'm not sure. So the Golden Gate Bridge, I'm not sure, but you can see that on a foggy day you don't see anything with the visible, but with the shortwave IR you can penetrate through the mist and the haze reasonably clearly, and you can see very clear image of the bridge here. The other is it's also used for example, detecting defects. So if you have an apple and you just look at it, if there is a bruise inside the apple or a defect, you can't see that with your visual light imaging. But if you use a shortwave IR, you can identify the spots where the bruises are inside. Similarly with counterfeit currency and things like that. So therefore, most of these are actually very practically useful, but they are not very keen on taking the temperature image. You are only looking at a visual image just like your normal camera, but at a wavelength which is probably helpful in conditions like fog, haze, and those conditions where the visual light is completely absorbed. So for scientific purpose and our purpose, we will be focusing mainly on the other two cameras, which are the midwave IR and the longwave IR. Midwave IR works in a band of 3 to 5 microns, again a slightly shorter band, but it's a very useful band in the sense that it's very sensitive to temperatures that are of the surface, and therefore we mostly use very high sensitive cameras in this particular bandwidth. Now the difference between midwave, long wave and the shortwave is shortwave was primarily, as I said, it is working based on the reflected light, whereas the midwave and long wave, they work based on the thermal radiation from the surfaces. That means that the camera can detect the heat that is coming from the surface directly, and not just looking at the light or visible or the reflected component of the light that is coming from the object. So therefore, now the sensor has to be capable of detecting the heat. Okay, so we look at the different types of sensors here. But the advantage is, before we go into that, is that the MWIR is very highly sensitive. It has a very fast transient response. That means they are suitable for imaging high speed events and also to measure very small temperature changes. So this is the sensitivity of the camera. This is quite good. And one problem with this is if you are using it outdoors too much, the ambient solar radiation also can interfere with the object, the radiation coming from the object, because the solar radiation is quite broad in different wavelengths, and it can interfere with the radiation coming from the object of interest, and therefore it can corrupt the actual the intensity that is received by the sensor. So this is more suitable for doing imaging of objects inside closed, inside indoor, indoors and so on. Okay, and the common detector that MWIR uses is the indium antimonide. So this is semiconductor material, and there are also other materials. So how do you choose this kind of semiconductor material? So again, you have to look at the wavelength of this IR that it is receiving and the band gap of the semiconductors, and accordingly you have to use those semiconductors which are most sensitive, the band gap of these semiconductors which are most sensitive to that particular infrared spectrum. That's why one requirement is you need to maintain the semiconductors at very low temperatures, as low as 70 Kelvin or 80 Kelvin, using cryogenic cooling. So only then this will be acting sensitive to that particular wavelength. At room temperatures, this may not be simply sensitive to that particular, the band gap will not be matching the frequency of the incoming radiation. So the camera that we have in our lab is also a high speed one, which is X6981SC, which is of this particular one. This is the last slide before we break. I hope the tea has come. You can just check. We'll just take a break after this. Yeah. So the other camera is the long wave IR, which is in the long wave band of 8 to 12 microns, and the long wave IR cameras actually are used mostly in the military operations, because what happens as you go to the Planck's distribution, you see objects which are in the having low temperatures close to the ambient temperatures, the peak in the emissive power is more sensitive in the long wave IR region. So therefore, if you are using long wave IR region to look at ambient temperature situations, so they are more sensitive in that. And if you want to distinguish some events or some objects which are close to the ambient temperature, they are also quite good at it. For example, here you can see with the visual camera, you can see a foliage and hardly anybody inside. But when you use the long wave IR, you can clearly see a person who is hiding behind the foliage here. That's because the person's skin temperature is slightly above the foliage temperature, and your long wave IR is quite sensitive to this particular temperature scale. And one of the things is the sensors with the long wave IR. There are also cooled sensors which are still using semiconductors, but most of the long wave IRs are uncooled cameras. So they use what is called as a bolometer. So a bolometer is nothing but, so whenever a heat falls on the material, so the resistance of the material correspondingly changes, and this produces a current. So you have a Wheatstone's bridge network. So if one of the arms of the Wheatstone's bridge has a variable resistance and the resistance changes, you produce a current, and then you calibrate the amount of heat that falls to the current that is produced. So this is the principle behind most of this long wave IR. So they are actually uncooled cameras. So you don't have to cool it to the extent you cool the mid-wave IR cameras. Although, so caution, don't think that all long wave IR cameras are uncooled. There are also cooled long wave IR cameras which can be used for much finer and fast transient events. But the general cameras that you get with long wave IR are all uncooled bolometer type. So just a schematic here which shows the brief working how the IR camera basically works. As I said, we are classifying IR cameras based on the IR wavelength bands, which are basically transmissive, or the windows in the atmosphere which are transmitting IR. So apart from that, when you look at IR cameras, the IR cameras are essentially having a detector or a sensor. So this is basically the eye or the heart of the camera, and you can have two types of detectors. Again, based on the wavelength, we have already mentioned it. So it could be uncooled thermal camera. For example, the long wave IR that I mentioned, A655SE, is a uncooled camera. So the uncooled cameras work on different principles. They directly sense the heat through some principles where the resistance of the element changes, and consequently the current changes, and then you have a calibration of the current proportional to the intensity of the radiation that is falling. So that is uncooled, where you don't have to have very expensive semiconductor materials to be used, and also you don't have to cool the semiconductor materials to very low cryogenic temperatures of 70-80 Kelvin. So these are maintained at room temperatures, and therefore fairly compact, lightweight, and also inexpensive. Whereas if you go to cooled cameras, so which are the ones which I talked about in the mid-wave IR spectrum. So for example, the X6981SE. So the cooled cameras use semiconductor devices and the principle behind the semiconductors. So, and they have to be maintained precisely at a temperature so that that material acts like a semiconductor with the defined bandwidth which matches the mid-wave IR bandwidth, the wavelength. So therefore, these work again based on principles of either photovoltaic or photodiodes or photoconductive devices, which are all basically what semiconductor principles behind the semiconductor devices. You can either have a standalone semiconductor device, or you have doped semiconductors like P and N. You form a junction, and then you use the depletion layer to produce the current and so on. So these are all separately classified as cooled cameras. And the advantages of using cooled cameras is, although they are bulky, they are more expensive. They're way more expensive than the uncooled cameras. They have very fast response with respect to time. So if you are capturing images which require a high speed, fast response, fast transients, you can use the cooled cameras. And the other important thing is, with the uncooled, you need many photons to fall on the detector, because the detector is basically sensing the heat directly. So for the heat to be substantially felt by the sensor, you need more photons to fall on the surface area, and whereas with the cooled cameras, just a single photon is sufficient to excite the semiconductor material, and therefore these are photon counters. They just can count individual photons, so you don't need actually too many photons to be exposed to the detector. So these are actually single photon counters. Okay, but again, as I told, you need to maintain this at cryogenic temperatures for this to be completely functional. So these are actually, therefore, advantages, disadvantages. You can understand that uncooled cameras also are very important, and they also have their advantages where you want to be having a portable cameras which you can carry in your bag, and you can go to a lab and just take some images and again move to another place and do that. And whereas if you want fast transients and then you are looking at a very high sensitivity, you need to go for cooled type of cameras. Again, so I'm just going to skip over this. Anyway, the presentation will show some of the details of what are the different types of sensors in cooled cameras. As I said, so these are all semiconductor devices, and then you can either use the semiconductor material where the incoming infrared beams in terms of photons in that particular wavelength can produce an voltage, and the voltage drop can be measured. So these are the principle behind the photoconductive sensors. And photo diode sensors and photovoltaic sensors, you have a P semiconductor, N semiconductor forming a junction, and automatically when you have a junction, you have a depletion layer. And then again, when the photons fall on these PN junctions, so the strength of the depletion layer, or the width of the depletion layer, can be controlled, and then you can generate current by the movement of electrons across the depletion layer. So this current that is produced can be calibrated to the intensity of the photons that are falling on the sensors. So this is basically a principle behind all the cooled cameras. And the ones that we have, the X6901SE is a photodiode sensor. Okay. And the sensor we detect semiconductor material was in indium antimonide. Okay. So coming to the uncooled sensors, so there are again different principles. You can have thermopiles, you can have bolometers or pyroelectric. Each one of them have different methods, but they measure the same thing. That means whatever heat that falls on the particular material is converted in some sense current or voltage difference, and then you correlate that to the intensity of heat that falls. For example, thermopile is more like a thermocouple. So you use the Seebeck effect. You have two dissimilar metals or semiconductor devices which forms a junction, and then you have in the sensor, you have so many of these kind of thermocouple materials one after the other, that it forms an array, and it can actually be, you can say this is like an array of thermocouples which are placed like a sensor, and which can locally detect spatially the variation in the temperature. The bolometer is the one which is most commonly used in the long wave IR uncooled cameras. The one that I was mentioning, A655SE, has this. So the principle here is that when the intensity of the radiation falls on the sensor, so the resistance of this element changes, and accordingly, so this resistance will be the variable resistor arm of the Wheatstone bridge, and this gets unbalanced, and you produce a current which is also proportional to the intensity of the radiation that is falling. And all this is internally calibrated, and they know exactly for that current what is the intensity that is coming in. And also you have pyroelectric sensors. Now the important part is we have talked about the different bands of IR, we have talked about cooled cameras, uncooled cameras, we have looked at the relative merits and demerits of each of these. The other important aspect is when you look at the sensor, so we are talking about the resolution and the pitch spacing. That means these sensor elements which are placed next to each other, what is the separation between these sensor elements. So Nambudiri was talking about the Fraunhofer diffraction phenomena, the Airy's disk phenomena. Unfortunately, the IR bandwidth, if you calculate using the expression given here, what is the diameter of the Airy's disk that forms when you take a point source and put it through a lens, and for a particular wavelength, what is the diameter of the Airy's disk that forms? It is actually approximately 2.44 times the focal number times the wavelength. So assuming the focal number is approximately 1 or 2, for the lens, if your wavelength is larger, that means the diameter of the Aries disc gets bigger. So this is a problem with IR cameras. IR cameras are forced to operate with longer wavelengths. So inevitably, the IR detectors seem to be limited, or the scanners seem to be limited by this diffraction phenomena. So, whereas this is not a problem with conventional visual optical CCD cameras. Okay. So, for example, just to give an example, if you put a wavelength of lambda equal to 10 micron, which is the long wave IR, and with a f number of 2.4 for a lens, you will get that the Aries disc diameter comes to be approximately 60 microns. So that means even if your pitch spacing between the sensor elements is less than 60, you are not going to resolve point image better than that. Correct? So whereas if you look at CCD cameras, so if your wavelength is 1/10 of this, approximately 1 micron, the diffraction limit comes to about 5 or 6 micron, and if your f number is about 1, so even better, you have 2 to 3 microns. That means the sensor is not, the current sensors which are having a pitch of about 3-4 microns are not limited still by the diffraction limit in the visual CCD cameras, whereas in the IR camera you are already limited by the diffraction phenomena. Okay, so therefore the best that you can get with most of the conventional sensors is a pitch spacing of not more than not less than 20 microns. Okay, so even if you have an f number of 1, these are the best lenses, best type of lenses with an aperture number of 1. So you can say that less than 20 micron is not very useful to resolve by the IR detector. So this is one very important point, and therefore most of the IR camera detectors have a pitch which is 20 micron. That is the threshold that they use, and that is another reason for the same resolution of equivalent resolution that you talk about with the CCD camera. So 4K resolution or something like that, you will have a much larger detector size in the IR cameras, and that's why the IR cameras look much bigger and bulkier than a conventional CCD camera. So this is a very important point that you need to know, that although you may have the same pixel size, pixel numbers, but the pitch spacing between the pixels, that is the actual resolution of a point image, is much larger in the IR cameras than that of the conventional CCD cameras. So these are terminologies which you already know. Resolution and frame rate is another important thing. I already talked about the resolution. You can have number of these sensor arrays. The array size can be like 1024 by 768. This is actually on the higher end. This is a clear HD image. But you don't get array size bigger than this, because the cameras are already bulky with this kind of an array size. So you don't get a 4K kind of a resolution with the IR cameras usually. And on top of which, you also have a frame rate, which is important. And we saw that the high frame rate cameras are usually the mid-wave IR cameras, and usually the cameras are also limited, by the amount of processing that they can do on the memory. So you cannot expect a very high frame rate associated with a very high resolution. So usually, when you want to increase the frame rate, your field of view gets smaller, and you have to use a smaller resolution to capture this, and therefore the frame rate and resolution are inversely correlated to each other. So generally, if you look at the IR cameras, they will give you what is the typical frame rate corresponding to the full resolution. So the full resolution, suppose here, let me say 1024 by 768, they will tell you the maximum frame rate as corresponding to this full resolution could be something like 100 fps or 50 fps. And now when you have a smaller window for the array, and if you go to smaller and smaller resolution or array sizes, you can increase the frame rates correspondingly, and you can even go to 10,000 fps with the, or 20,000 fps with the high speed cameras. Okay. The other important aspect of choosing IR cameras is, which many of the students overlook, is the noise equivalent temperature difference, which is called the NETD. This is an indicator of the sensitivity of the camera. So what it tells you, suppose I have a temperature isothermal surface completely uniform, which is at, say, let us say 300 Kelvin, And if I use the IR camera, so it has inherent sensitivity. Suppose instead of 300, if I make it 300.001 Kelvin, at some point, if the camera is sensitive enough, it should be able to show that this particular point is slightly different from the rest of the background. Okay, that means you are trying to separate the signal from the noise. So that shows that if the camera is very highly sensitive, that means the temperature difference that which it can detect, the minimum temperature difference with which it can detect, if it is as small as possible, then it can have a good thermal contrast. Okay, that means you can see the object clearly from the surrounding background or the noise. So this is called NETD, and if your NETD of the detector is as low as possible, that means the sensitivity is very high. Usually the manufacturer gives you a value of NETD as good as 20 or 30 millikelvin. Okay, so that means with 30 millikelvin difference you can identify two objects. Otherwise they will all be the same, they all look identical. But if there is a 30 millikelvin difference, you will be able to see the silhouette of this object from the surroundings. And but this is too good. Actually, sometimes it's too good to be true. When you test it for yourself, you will understand that these numbers are only the best numbers that you can get at very ideal conditions. Okay, so you have to check this NETD yourself. So the simple way of doing it is you take a series of 300 images of some surface which you coat it with black, so that the black coating will improve the emissivity close to 1 and you get the maximum possible emission from that particular surface. So when you take a series of 300 images and you calculate the standard deviation at each pixel, and you can deduct what is this NETD. Okay, so every time, so it is actually the same image, the same object, same temperature and the same resolution. You are just taking 300 of these images and then you are trying to see how the camera is able to, how sensitive it is to resolve any fine changes in the temperature, and then you calculate the standard deviation of it. So this will give you the NETD, the true NETD. And many times, even if the manufacturer gives you an NETD value of 30 millikelvin, when you do this by yourself, you will find that it is of the order of 80 millikelvin or 100 millikelvin. So then you have to use some techniques in image processing where the effect of this higher NETD, which is introducing some thermal noise, actually has to be minimized, and I will show you that. So this is one such technique where you smooth the data to reduce the NETD. So in this particular algorithm, you are taking the temperature snapshots at different time instants. For example, the temperature at the current time instant is this. So this is the field. Okay, so this is not just at one point. This is the complete information of all the pixels. Similarly, you have the temperature snapshot at previous time t minus 1 and 1 at before that t minus 2, 1 later t plus 1 and t plus 2. Therefore, you have 5 snapshots. You can use a weighted average to calculate the average value of the temperature at a given pixel, and then you again do a time averaging. Then you apply a Gaussian filter so that you can smooth this at different values of the standard deviation. And you can check at different values of standard deviation, that means how the distribution is broader or finer. You can see how this average pixel temperature changes, and accordingly you can find that if you do this kind of smoothing procedures artificially, you can bring down the NETD values. Although when you check the NETD is about 100 millikelvin, by doing this kind of smoothing processes, you can bring down the NETD and make the temperature output more sensitive than what the manufacturer is giving you. So these are some comparisons of specifications between the two cameras I was talking about. One is a long wave IR camera. The one that we have is A655SC. The other is an MWIR, which is X69. So the model now is changed, number is changed to 6980SC. So earlier, previously it was called 6900SC. And these are the different types of detectors they have. This is a microbolometer and this is indium antimonite. Spectral range, you can see that this is long wave, this is mid wave, and all these are known. What is important is the frame rate. You can see that this is the frame rate at full resolution, right? The full resolution, the pixel array, maximum pixel array, this is 50 Hertz, whereas this is a higher frame rate. You can see 1000 Hertz. So if you reduce the pixel array size, you can increase this to a very high frame rate as high as 20,000 and so on, 20,000 hertz and so on. And you can also see the detector pitch. So it's about 17 micron here, it's about 25 micron. This is what I was talking about. So these sensors are all diffraction limited. So therefore, the best that you can get with most of the conventional cameras have about 20 microns, not less than that. Okay. So the other important aspect is the lens, use of lens for these cameras. You have to keep in mind that when you are having a lens for your infrared detector, so these lens should be transparent to IR. So there are different materials which are used depending on the wavelength band of these cameras. And you can see, for example, glass can be used as a lens directly, but provided you are using a shortwave IR camera. For the MWIR and LWIR, mostly we use germanium because germanium is a very good transparent material at wavelengths for both mid-wave and long-wave IR cameras, whereas sapphire is transparent in the mid-wave, but again they are not that good at long-wave IR. So the germanium is one good material. The other is zinc selenide, but these are expensive materials. This is actually transparent in all IR wavelengths, right from short wave, mid wave, long wave, so they are completely transparent. And also zinc sulfide. Okay, calcium fluoride is also used quite common. They are transparent to both short wave and mid wave IR regimes. Okay, so I think this is some information. I think again this is coming from the basic optics, that if your if your transmissivity is increasing, the transmissivity of the material is large, so it tells you that this also leads to a large reflectivity at the same time. So therefore, so if your reflectivity is large, the overall transmittance can come down. So some of these lenses which you think that they are highly transmissive also are highly reflective. So in the process, if your reflectivity is very large, so your overall transmittance can come down to some extent. So therefore we need to coat these lenses with anti-reflection coating. For example, if you look at germanium, the normal transmission is about 0.47. So it's not very high, but reasonably good enough for the IR bandwidth. And if you coat it with anti-reflection coating, you can improve the transmission coefficient to as high as 90-95%. So this is why most of the lenses for IR have a anti-reflection coating on top. Now let us now come back to the actual thing, that is how do we use these IR cameras to measure temperature. So I am just going to quickly look at two scenarios. One, I am going to use it to measure the surface temperature. The other is to look at liquids and look at interfaces and how do I measure the temperature of these interfaces, which is also very important. So when it comes to any temperature measurement, whether it is surface or interfaces, if you just put the IR camera in front of the object, so it will give you some temperature readings, but you cannot just take it as it is, because there are many things. For example, you do not know what is the emissivity of the material, number one. And again, you need to make sure that you put the camera exactly in a fixed orientation and at a fixed working distance, because that the intensity that is emitted from the object is going to be a function of the distance as well as the orientation, because radiation has an angular distribution. Okay, so therefore what we usually do is we fix the IR camera at a position at which we do the experiments, and before we start taking the surface temperature measurements, we first have to do what is called as calibration. So how do we do it? For example, let us say you are going to do some temperature measurements on copper surface. We take a copper block, we insulate it, we have a heater which is going to maintain the copper at some predetermined temperature values, mostly isothermal, because copper is very highly conductive. Very immediately it reaches to an isothermal state. And then to maximize the emission that is coming from the copper, we try to apply a black coating on top so that the emissivity of this material comes close to 1. Because you cannot just plug in the table values of emissivity that you find in textbooks into the camera and expect the camera is going to give you the correct measurement of temperature. Because as you know, even for metals like copper, there is a wide variation in emissivity between an unpolished surface to a polished surface. The polished surfaces have high reflectivity and low emissivities. So therefore, you cannot expect the value of emissivity of the same material to be the same. Depending on the machining process that you do, it can vary widely. So what we generally recommend is we have to do a calibration with a thermocouple to be more accurate. So we can do this to estimate the emissivity of the material, or we can also build a calibration like this where we get a curve fit between the actual temperature using the thermocouple versus the temperature that is obtained using the IR camera. And when we do the experiments with the same camera, at the same orientation and so on, we reconvert back the IR temperature that the IR camera gives back to the actual thermocouple temperature. So these are the true values. Okay, so this is a very important step, and we have to do this for all kinds of temperature measurement, whether it is for surfaces or interfaces. Okay, these are some results that from our own group where we have studied the heated wall jets. The heated wall jets, which are usually used for cooling, the combustion chamber liners in aircraft gas turbine engines. So they are subject to very high temperatures in the different zones like the primary, secondary and tertiary zones. So we use bleed air from the compressor and then we try to cool the combustion liner. So here what we have done is, of course we didn't do this at combustion temperatures, we just heated the air above the atmospheric temperature, ambient temperature conditions, and then we use the IR cameras to image what is happening at different time instants. So these are the temperature contours for different types of configuration of these jets which are issuing out of these orifices. So we have varied, for example, the pitch spacing between the jets here, and you see the kind of distribution and what happens when you increase the pitch further. So it gives you a complete temperature field information, and before we get this IR data, we calibrate it in situ. So the in situ calibration is something like this. The in situ calibration is very important for dynamic temperature measurements. Because as you see, what happens is when you do a static temperature calibration, so it gives you at a fixed point what is the relation between your IR temperature versus your thermocouple temperature. But in an actual flow field where there is a wide range in the variation of temperatures and also a very fast transient response that is happening, it is better to keep multiple thermocouples positioned along, and then at each time instant we get the temperature data at these values, we get the IR data, we have a calibration at that particular time instant, and then we interpolate all the other temperature field to fit it to this calibration. So like that, for each time instant we use the corresponding calibration at that particular time instant, so that these are more accurate, and this also gives a fast response temperature information. So this is called in situ calibration, which we adapted in this particular study. So because we were looking at information at different time instants, from which we were using a semi-infinite approximation to extract the film cooling effectiveness and things like that. So we wanted the data to be also quite sensitive to this. Now the next information you can get from these IR cameras, this is very important, is heat flux measurements. The heat flux measurements are something that you usually do with either using a heat flux meters. Nowadays people don't use heat flux meters that much, or you use thermocouples itself and you use the Fourier's heat conduction equation, and you either do a one-dimensional heat conduction approximation, or you use the boundary condition of temperature, you do a numerical study and get the heat flux. So these are all intrusive techniques, using thermocouples. So what we do with the IR is very interesting, in the sense it's completely non-intrusive, and it can also give, on top of the temperature field, it can also give you what is the heat flux field information. So for example, here we just do a droplet impingement on a thin foil heater. So the thin foil heater is very useful for making the approximation that you can neglect the heat conduction across the thickness of the foil, because this is of the order of few microns, and therefore you can apply an energy balance. So whatever energy balance here, it tells you that there is certain amount of heat generated within the foil. We actually heat the foil by Joule heating. So we have a copper bus bars, and you have a foil which has a very high electrical resistance, so that it can heat very quickly, such as stainless steel or Inconel. And then we write the energy balance, wherein we know what is the amount of heat that is generated inside, what is the amount that is stored over a period of time, and also what is the amount of heat lost to the surroundings, by convection or mostly by convection and radiation. And on the other side, if you have a drop placed, so you know what is the amount of heat that will be also going to the drop. So this is a complete energy balance. And from the temperature information, so we know what is the conduction in the lateral directions. We can calculate that like this. So we can discretize the complete field information of temperature for each pixel on the surface, and we can calculate the conduction in the lateral directions. And applying the energy balance, we can now estimate what is the heat that is going into the drop. Okay, so this is a heat flux field again. So it is not a one point information what you get from thermocouple. So this is very useful, because for example, I'm just showing you. So this is the information what we get from a drop which is impinging on a heated surface. You see the temperature profile is something like this, and at the same time you also saw that there is a heat flux signature, and you can also identify regions where the contact line is. Yesterday we were discussing about it, where the contact line region can be identified by local region where the heat flux can be very high. Okay, so things like that which you cannot otherwise detect with a conventional technique using thermocouples can be easily visualized or imaged using the IR camera. So this is very, very important. So it's not only temperature imaging, but also getting the heat flux information out of the temperature distribution is a very important aspect of IR imaging. Now when it comes, very briefly in 5 minutes I will quickly complete the IR thermography of liquids, which is also a very important topic. So IR thermography has also been used to calculate the interface temperature measurements, for example of evaporation of sessile drops, which is of the order of scales of few millimeters. And you can also look at interfaces which are of the order of scales. And then if you look at, for example, remote sensing applications in ocean engineering, you're looking at scales of the order of meters to kilometers. In all these cases, the infrared imaging can still be used to get the temperature distribution on interfaces. But what is important, this is the principle behind getting the temperature data from the interfaces. You should understand, when I put a drop like this and I put an IR camera on top to get the interface temperature, so the IR camera is getting the emission from different sources. So one is a reflected component of the ambient radiation, which is reflected to the detector. The other is basically the component that is coming from the top of the interface of the drop. The other that is coming from the substrate. So if the substrate is at a high temperature, for example, so that information also can penetrate through the liquid and come. So therefore, the camera is detecting all these three components. One is the ambient component, which is reflected. The other is from the interface. The other is from the substrate. So therefore, you have to be very careful what kind of liquid you are using when you do this interface temperature measurement. For example, if you use water, okay, and let us say you have different thicknesses of water. So the transmissivity of the liquid depends on the thickness of the liquid, right? So the thicker the liquid, it becomes less and less transmissive. So if you take water, which is of about 1 micron thick, you will see that the transmission is actually almost. So this is not correct. It should be, yeah. So this is, I think this should be the other way. So the transmission of water should be almost 0. So I think
At 1 micron, it's okay.
It's 1 micron.
The 1 micron is the
1
black
millimeter
one.
would be 0.
Yeah, sorry. So the 1 millimeter is 0. So that's correct. So I was just looking at this. So the 1 millimeter should be almost 0. Okay. Whereas 1 micron, it is quite transmissive. So when you are taking an image of a drop interface which is of height of 1 micron, you may still see something transmitting from the substrate and reaching the camera. Whereas if it is of the order of 1 millimeter, you are not allowing anything to transmit, and whatever image you get, it is purely from the interface. Okay, so this is a very important aspect. Whereas if you look at other fluids which are also quite volatile, like ethanol, FC72 and methanol. So their transmission is much higher than that of water even at 1 mm. So for example, even if you take about 1 mm, so you can see the transmission of, this is in terms of emissivity, which is 1 minus the transmissivity. So you can see the transmissivity of these ethanol, methanol and FC72 are higher. So what you will see by that, what the detector sees is actually a signature of what is within the depth of the fluid and not exactly on the interface. So therefore you have to be very careful. You cannot claim that if I get the interface temperature of water, so I can use the same technique to get the interface temperature of ethanol. So there you might be actually seeing the substrate temperature and not the interface temperature. So this is very important. So generally for an opaque liquid like water, we also do the calibration like this. There are also other effects for which you have to correct. When you take a drop, for example, if you are imaging from the normal distance, so you are basically the emissivity the emission that is coming from the drop to the camera is normal, and the reflectivity in that particular direction is 0, you get the maximum emission. So the emission is also direction dependent. So if you are using the same camera to see the emission from the curved surfaces at the right and left extremes, you might actually see a different value of the emissivity. So you have to correct for the effect of curvature also, because the reflectivity changes with the angle. So accordingly, this kind of image processing has to be done for curved surfaces. Okay, for example, my student was so he completed his PhD couple of years ago, and he is now doing postdoc at Darmstadt with Peter Stefan. So he has done a beautiful study of evaporation of water drops. So in which he was simultaneously using both the visual camera as well as the IR cameras. And how IR cameras helped here in the visualization, I'll just tell you. When he was first using the IR camera, so he was just taking a simple hydrophilic surface, and he was doing this first at normal temperature, then he heated it to 80 degrees. Then he was surprised to see there was an IR signature of some vortex pattern which are moving around quickly within the liquid, and we found that this is coming from the interface, because water is completely opaque at this particular thickness. So this is completely happening. So there is some internal currents which are happening, and it is leaving a signature on the interface. So this is what we saw, which later drove us to further investigate what happened with this particular pattern. We also looked at hydrophobic surfaces. More interesting, we saw that these patterns are having a very rigorous oscillation happening at the interface, and very fast oscillations. So later we investigated this with a micro PIV, and we found that there are a lot of cells which are forming inside, and we attributed these cells to the Marangoni effect, because when we heated the drop with the substrate, so the surface tension, there is a gradient of surface tension along the interface, because the surface is at a higher temperature than the apex of the drop. So your surface tension is lower close to the surface than the apex. So in the net effect is to drive a flow from the low surface tension to the higher surface tension. So therefore we had a circulatory pattern which was forming a kind of a clockwise vortex pattern inside, which we attributed to the Marangoni effect, and these was producing velocities which are order of magnitude higher than the cells that usually observed due to buoyancy. So initial time instance we found these convection cells were predominantly due to the Marangoni effect. Later as we went, we saw that slowly the buoyancy effect took over, and then these cells disappeared from the infrared imaging. But internally when we did the micro PIV, we saw the circulation pattern reversing and anti-clockwise vortexes being formed, which is your conventional natural convection. So therefore, just I'll stop here. These are some of the images that are coming from Brutin's group. So they have, and Sefian's group, they have done imaging of other drops like ethanol, methanol and FC72, where you can see that these kind of beautiful Marangoni cell patterns, cellular patterns coming, and these are not exactly coming from the interface, they are also coming from the substrate and within the droplet, because these are transparent to IR. So these are things which are important when you do the imaging. So on top of your conventional imaging, the IR also gives you some perspective of flow visualization, so which can help you to further investigate and do your conventional imaging techniques. So for further reading, I stop here. You can use this particular textbook, which is a fairly good comprehensive textbook on infrared imaging, specifically for fluid thermal problems. And with that, I thank all of you for attending this session. It's slightly short over the regular time, but I hope it was useful.